Hello, welcome to my third video on intermolecular forces. My name is Dr. Kim. So in this video we're going to look at the third force, which is the strongest of these three forces, the hydrogen bridge force. There's some key words that we should go over for the hydrogen bridging force. First of all, this is also a permanent force, just like dipole-dipole. So it's not like the London force. This one is permanent, and it involves polar molecules, just like the dipole-dipole force. In fact, you can think of it as a subcategory of the dipole-dipole force. So it involves polar molecules, but these polar molecules have to have an H bonded to an N, an H bonded to an O, or an H bonded to an F. So the polar molecule has to have an HN or O or F bond. Sometimes we call that NOF. So an H has to be bonded to N or O or F. Water is an example of a substance that has the hydrogen bridging force. So here we have two water molecules, a hydrogen bonded to an oxygen, bonded to a hydrogen, and here's a second water molecule, hydrogen bonded to oxygen, bonded to hydrogen, and we have our two lone pairs. So now if you remember, all intermolecular forces are attractions between the delta plus end of one molecule and the delta minus end of another molecule. And the attraction is between these two ends of two different molecules. This attraction equals the force. So here, hydrogens are a little bit positive in water, oxygen's a little bit negative in water. So this hydrogen on the second molecule is a little bit plus, and it is attracted to the oxygen on the first molecule. Again, it's an H bonded to an O in the molecule water that enables us to have this hydrogen bridge force between the H of one molecule and the O of a different molecule. Again, you have to have at least two molecules to have a force, because the force is between the molecules. So water displays the hydrogen bridging force. Now, we've talked about all three of the forces, so let's review. The London dispersion force is for non-polar molecules and atoms. It is temporary, and it's often seen in gases. The dipole-dipole force is permanent, and it is between polar molecules. And then the hydrogen bridging force, also permanent, with polar molecules that have an H bonded to N or O or F. So now that we've learned about these three intermolecular forces, let's answer a question. What is the strongest force in samples of? Number one, carbon monoxide. So carbon monoxide has a CO bond. Is that a polar or a non-polar bond? Well, C and O are both non-metals. They're on the non-metal side of the periodic table. They also are not the same element, and one of them is going to pull the electrons closer. Now remember, we have one element who pulls electrons closer than anybody. Do you remember which one that was? If you said fluorine, you're correct. Fluorine pulls electrons closer than anyone else. And the closer you are to fluorine, the better you are at pulling electrons towards yourself. So out of carbon and oxygen, who is going to pull the electrons closer? Well, oxygen. Oxygen is closer to fluorine. What's the charge on the electrons that oxygen is pulling closer? Negative. So oxygen is a little bit negative, carbon is a little bit positive. So this CO bond is polar. So what is the force that goes with polar molecules? If you said dipole-dipole, you are correct. So number 1 is dipole-dipole. Let's move on to number 2. C2H6. Oh boy, I don't want to draw that Lewis dot structure, but I don't have to. What do we know about the CH bonds? What do you remember about CH bonds? Are they polar or nonpolar? If you said nonpolar, you are correct. So if your chemical is made of nothing but carbon and hydrogen, which is called a hydrocarbon, then it's nonpolar, because all the nonpolar bonds total up to being nonpolar. You can't create a polar molecule from nonpolar bonds, so anything with C and H has to be nonpolar. Which force goes with nonpolar molecules? If you said London dispersion forces, you are correct. Number 2 is London dispersion force. Number 3, NH3, which is ammonia. Now for this one we need to draw the Lewis dot structure. So you would add up your electrons, valence electrons. Nitrogen has to be in the middle because hydrogen can't be. Hydrogen only wants 2 electrons. So nitrogen has to be in the middle with the 3 hydrogens around it. Everyone needs to have 8. Hydrogens want 2. Hydrogen already has 2. So does this hydrogen. So does this hydrogen. Nitrogen currently around it, it has 2, 4, 6. So it needs 2 more. 8. And if we did our valence electrons, it's 5 plus 3 times 1 equals 8. So 8 valence electrons, there's our Lewis dot structure. Now, is this a polar or nonpolar molecule? Well, we have NH bonds. NH bonds. Well, hydrogen and nitrogen are nonmetals. Who's closer to fluorine? That's right, the nitrogen is. So nitrogen is going to pull those electrons close. And so our little arrows are actually going to point towards the nitrogen. So I have 3 arrows, all pointing in towards nitrogen. Do those arrows cancel out? Are they all equal and opposite? Okay, no. Plus I have a lone pair up here, and there's nothing opposite it to balance out with that either. So this molecule is in fact quite polar. Now you may have noticed something obvious. What kind of bond do we have here? The NH bond, that's correct. And what do we know about forces and NH bonds? If you said hydrogen bonding force, you are correct. We are polar and we have a hydrogen bonded to an N or an O or an F. That gives us the hydrogen bonding force. So polar molecules with hydrogens bonded to N or O or F have hydrogen bonding force. That's number 3. Our last one is Cl2. Why is there a 2? If you said diatomic, you're right. Chlorine is one of the diatomics. Have no fear of ice cold beer. Cl for cold, it's diatomic. So here we have chlorine bonded to itself. What do we know about things bonded to themselves? If you said non-polar, you are correct. When you are bonded to yourself, you are non-polar. That's a non-polar bond because chlorine's pulling the electrons equally as hard as the chlorine on the other side. It's like having a tug-of-war with yourself. There's no winner. So it's non-polar. And what force goes with non-polar molecules? If you said London, you are correct. London dispersion forces is the answer for number 4. All right, good luck with your intermolecular forces.